Okay, so now the question is, first of all, we will talk about the units, the different types of units, then the metric system, then, the exact numbers, the inexact numbers, uncertainty in the measurements, what does that mean? Then scientific and standard notations, significant figures, calculations, conversion factors, and equality. And this relates to the dimensional analysis. Dimensional. So hopefully we can finish all of it today. Then density and the temperature. So let's do first of all, let's talk about units. So you guys tell me, when we take measurements, right? We take measurements in terms of numbers, right? Number, like how many students are in this class? There are like 48 students or 45 students. So that's a number. And that number 45 tells us the number of students. 45 could be the room number. 45 could be the temperature of the day. 45 could be the number of pages in a book. 45 could be the page number, right? So 45 could mean anything. But now you guys tell me, in terms of units, what are the different types of units that you know of?
Volume.
Okay, the unit of number one, volume. Okay,
Mass.
mass, and
Length.
very good, and
Temperature.
temperature. Excellent. Anything else?
Density.
Very good. And there are many more. Anything else? One or two more. There's also a unit for solubility. Solubility. Then there's units, in terms of like conductivity, like how fast, or how quickly a substance, witty. Okay, so we won't look at these units here. Just focus on the common ones. So volume. What are the units for volume? We talked about this yesterday, so this is just a quick review. Yeah, volume is
Liters.
okay, guys. Here's the thing. Let's do this. I mean, if you guys have a noise at the background, then best is that you guys mute yourself. Students are already muted. And so I like the classroom participation. So you can unmute yourself and speak. Okay. But just try to avoid the background noise. Okay. All right. So volume, liters, milliliters, right? Deciliters, microliters, right? And then what are the other units? These are these milliliters. This you see milli, deci, micro. These are small units. Big unit that you know.
Gallons.
Gallons, very good. What else?
Ounces.
Ounces, good. And when we say ounce, okay, that's fluid ounce, because ounce can also apply to solids. What else? Anything else,
Pints.
Pints, very good. So small unit, pints, excellent. Okay, next is mass. Let's look at mass.
Kilogram.
Grams, kilograms, milligrams, right? Micrograms, and give me a big unit or some other unit that you know.
Pound.
Pounds, very good. Pounds and ounces. So we have the fluid ounce for liquids and the ounces for just the solids. Okay, what else? Anything else, Large unit.
Liter.
These tell you, just give you a picture that way. If it's tons, that means it's a big amount. But if it's a pound or like a small, like a milligram, that means it's a small amount. So these units themselves give you like a visual picture of, the number and like how much the substance would be. Okay, now let's look at the length, the unit of length.
Meter.
Meters.
Centimeters.
Centimeters.
Inches.
feet, kilometer,
Miles.
So these, okay, what about the temperature?
Celsius,
So
Fahrenheit.
Kelvin.
Fahrenheit, and for Kelvin, you don't write degree, you just leave it K. Okay, density, as we talked about, it's grams per milliliters when you're looking at the liquids, and grams per centimeter cube for the solid.
solid,
There are others also, other units also, like boiling points, obviously will be in degrees Celsius or degree Fahrenheit, melting point, freezing point, right? And there are many more different units, but let's focus on just to give you an idea. So now, when we talk about these units, two things are there. One is that there should be a uniformity, right? These measurements are being done in the past all over the world. Everybody was just doing their own measurements. Like, for example, if in the historical times, they used to do big cubit. Cubit is like from this finger all the way till your elbow. So this cubit measurement of things, there's not uniform. A small person versus a medium-sized person versus a large person could have these variation in the cubit alone. So in the kingdoms, it was different. Like, okay, the cubit of a king, that is like a reference, and everything is measured according to that. But as the kingdoms dissolved and the businesses kind of, were overlapping, or people were, traveling, and things became more universal, then we needed to have some kind of a universal system. So we came up with this, first of all, with just understanding the meanings. Okay, so this metric system was designed where we said, okay, anything that is big, that is mega, and it will have M. Kilo is again big. Okay, so these are big units. So what does mega mean? Anything multiplied by 10 to the power 6 would be mega. Or anything, any number multiplied by the 10 raised to the power 3 would be kilo. So again, these are big units. But if you have small units, then there you go deci. Now, what does deci mean? It is 1/10 of something, whatever that base unit is. 1/10 of, now these can be applied to the volumes, these could be applied to the mass, these could be applied to length. So, so it just gives you a picture of whether you're looking at something big or small, and in what magnitude is that. So when we talk about like mega million, so in your mind, you get that picture of mega $1,000,000, like so many dollars. So those things. And if you just say thousands of dollars, when you talk about a millionaire is million, like a 10 to the power 6, like a very rich person. So those type of things. Okay, deci, again, 1/10 of the base unit, centi, 1/100th of the base unit. And so these are all fractional units. Milli is 1/1000th, and the micro is similarly. So if you look at it here, the fractional units will have an inverse number, like 10 to the power -1, 10 to the power -2, 10 to the power -3. So this means these are smaller numbers. So here's a little bit from your prerequisites. The negative number, negative exponent is small anyways, but here 10 to the power 1, -1 is bigger than 10 to the power -2. 10 to the power -3 is smaller than 10 to the power -2. Okay, so in other words, this 10 to the power -12 is like a really, really, really small number, small amount. Okay, so keep that in mind, that negative exponent means a small number, but a positive exponent means a big number. Keep that in mind. Okay, now, next thing we are going to look at is that we wanted to, like I said, we wanted to bring equality. Okay, we wanted to bring equality. And what is that equality? Equality is, let me just close all these. What is this we're doing here? Why is this not? Oh, sorry. Okay. So equality is, we wanted to bring uniformity in these measurements or the units. So they said, okay, fine. We have to bring like, okay, There is a metric system, and then there is this, like, one is the metric and the other is the SI system. The relationship to there's an English unit, which was more universal, obviously for historical unit, historical reasons, and then people were also using their own thing. So we said we need to bring a uniformity. So what is that uniformity? So we said, okay, if anything that is 1 meters and you're measuring something in 1 meter, it is going to be equal to 1.094 yard. So this is called the equality. Okay, 1 centimeter equals to 0.394 inches. So 1 millimeter is point. So similarly, these equalities, they make the they make the units like same. If so it's like if people are whatever the measurements that, so in other words, we would have a universal same measurement throughout. Now look at now look at these relationships in the metric. So if you have how are 1 meter related to millimeter? So 1 meter is equal to 1000 millimeter. So in other words, when we go up here, how are these guys interrelated? How are you relating these mega, kilo, deci, centi to each other? Even in that. So even in that, these units come into play. Now, you don't have to memorize them, but you should, this is your handout. I printed it out. Okay, I printed it out. I have it in the labs, but if you have already printed out, good. If not, then you can take it from me in the lab. I'm distributing it, and you can add from your side more, because this is just a small table I had. Okay, so same is the case. Look at these meters, milliliters, and deci centimeter cube. So I'll be honest, we don't use in chemistry labs, we don't use for us, we don't use like these very like smaller units or very large units. The basic things that you're going to need for your lab is how to convert grams to milligrams and milligrams to grams, how to convert milliliters to liters and liters to milliliters. So we'll show you how that is done. But you will be needing these equalities in order to do the conversions, in order to do the dimensional analysis. Okay, so refer to these. So similarly, these centimeter these temperature scales, and here are your other calories, kilocalories, joules. So that's the units for the heat. Okay, these are the, again, milliliters to fluid ounces. So we will be referring to these. So this is one thing. Okay, now back to our this thing here. Once we get the units, next thing we are looking at is so we talked about the metric system and the prefix, and now let's look at the exact and the inexact number and the uncertainty. So exact numbers are those numbers which don't have the decimal, or even if they may have a decimal, they are like, they are exact, there is no uncertainty in. So here, let me just write this down. So this was one part we did on the units. So the second thing was here for the prefixes, we referred to the handout. Okay, so we already covered that. Next comes the third part, which is the exact numbers. Now, simple exact numbers are like, for example, students in the class, so 45 students, it can be 45 and a half students, you can't, you know what I mean? So 45 students, how many trees there are? There are 10 trees in the compound or 10 trees in the yard. So 10 trees, so 10 is the exact number. How many bottles of milk? You can't have 1.5 bottle of milk, right? So bottles of milk or bottles of juice or whatever, that number is an exact number. So let's say this is like, there are 20 bottles of milk. So this is an exact number. Okay, so this is one thing, one way when you measure, when you count things. Okay, so exact numbers generally come when you're counting, when you count. Okay, now sometimes when you're measuring, then also measuring, so let's say you are measuring up to 25 point, if you have, that means when you are reading the temperature or you're making a reading on something, yeah, so it should be exactly 25, it not more than 25. It should not be 25.0 or 25.01 or 25.1 or something. So this is another way of looking at the exact number. Let us say, and then so let us say some whatever the unit is here. Another exact number could be 25.1 and then nothing after that. So that means that whenever you are taking the measurement, that your reading should be 0.1. You should read up to 0.1. Okay, so this is also like you have to read up to one place after decimal. So that is like, in a words, counted in measurements. One place after the decimal is considered or counted. So commonly we use the word counted. Okay, so here just 2 places before decimal are like counted. 2 places before decimal. Okay, so this is how you measure the exact numbers. Next comes the inexact number. Now inexact numbers are where there is some level of uncertainty. So inexact, so this is exact number. Inexact means that there are there's some uncertainty is built. Now, uncertainty, how does the uncertainty come, first of all? You guys tell me. How does the uncertainty come in a measurements? Those people who are present in the class also. What do you think? From where would the uncertainty in measurements come? Why or from how would the uncertainty come? Yes? Yeah. Estimate, okay. When maybe you are trying to do some estimation, very good. Anything else? Okay, maybe some errors also can come in, right? Next is, who is taking the measurement? Who is taking the measurement? Now, what kind of people take measurements? Who all work with numbers or who all do the measurements? Who? Say that again. Yeah.
Construction worker.
Very good. So construction people do the measurements. Very good. What else?
Tailor.
Scientists.
Who else?
Tailor.
Tailor. Very good. Who else?
Accountant.
Accountants. Excellent. Yeah. And with the accountants come many other, bankers.
Would it be just anyone in general working with numbers?
Absolutely. Anyone. Like we work with numbers
Chefs.
every day. Yes, we work with numbers every day. I mean, think about it, like Uber drivers. What is the fare? How long is it going to take? At what time will I be dropped at some place? So Lyft or Uber drivers. Or in how much time is a bus coming, or these transportation people, BART, 10 minutes, BART is 10 minutes late, so at least that, so those things, transportation people. What else? One or two more. Yeah.
Medical field. Doctors, nurses.
Absolutely. If the doctor says you need to take this medication, and the pharmacist and doctors, they and the nurses, they all work together, and then they say, okay, this person needs to take these 4 pills like 4 times a day, once each, one pill every 4 hours or something like that. So doctors, nurses, all of the medical field is full of numbers. Okay, one more thing, one more person who takes, I mean, yeah. Think about the people who are astronomers.
Engineers.
All kinds of engineering. Like, come on. I mean, people who made these devices, these computers and iPads and iPods, I mean, look at this pencil, this Apple pencil. Somebody decided it has to be only this length. Why can't it be?
Chemists.
So, what was that again?
Chemists.
Chemists, very good. Politicians,
Physicists.
physicists, yeah. So that's all in scientists. So politicians also, social scientists. They're all the time taking these statistical, data. So social scientists or uh, social politicians, or you get an idea. So anyway, so these people are working with numbers. They are all working with numbers. So for them, these numbers have their own meanings. And now comes the question. The chefs, they can ballpark, and they always do. Most of the time, they ballpark a lot of things, right? I mean, I don't know if you've seen that hell on, what is that, kitchen on fire? Hell on fire or whatever it is. You know how they sometimes use their hands and like they just sprinkle the salt. So why
Mhm.
not it's just a whole handful of salt? Why it's just a little bit using your fingers? You see that? So it's like kind of they have an idea, some estimation in their mark. So they ballpark a lot, like people who are chefs. So for them, like the level of uncertainty is like very flexible, so so when you estimate, you are bringing in some level of uncertainty and some level of error also, right? But think about these people who are accountants. I mean, come on, accountants, can you deal with uncertainty there? No, that's a problem. So for them, very specifically, when it comes to money, two places after the decimal means a lot. Okay, you have these numbers when you're doing these calculations, right? You look at the you look at your what is it called, the calculator. You see on the calculator so many numbers, you see, right, after the decimal. But for people who are bankers and accountants, for them only two places make sense, right? That's the digits, when hundreds. And so two places after decimal is going to make sense to them, and all the other numbers are just two places. So that's one piece for these guys. Next is, look at these people who are like, same as the case, tailors, scientists, scientists and construction workers. Look at these. This is more like construction. For them, some places after the decimal are important because their precision comes into play. So some places, and how many places after the decimal, it all depends upon what they are measuring, like for example, if they measure these buildings, so for them, certain places after the decimal, they have to stick to that measurement. They cannot like say they cannot round up, they cannot round down, because if they in bring in some kind of like like what do you call, like if they're not exact in their measurements, then the structure will fall. They won't have the similar, same story with the engineers. They won't be able to make the machines. So for them, so let me just write this down. Some places after decimal is important. And how many places after the decimal is important, that depends on their what they're measuring and all those things. But there is some level of precision is very important. Okay, so precision comes into play. Same is the case, like for example, now look at these astronomers. Astronomers are looking at these stars from very far away, and so yeah, you're measuring, this is a unit that they use, light years. Now they can just kind of estimate here. We say, okay, this sun is about 37 light years away from this earth. It could be 37, it could be 36 and a half, it could be 37.1. So you see that's again, that whatever measurements you're doing, it depends on who is taking that measurement, who's defining the definition of how far you can go after the decimal, how many numbers you need to have in the measurement. All that is governed by the individual taking the data. Okay, all these people, any one of these. So with that said, Now, with you guys, when you're working in the labs, yes, you are going to, as chemist, generally for us, two things for the chemist. Chemists, generally, two places after the decimal is considered like kind of acceptable or normal. So generally, two places after decimal. Okay, so this is one piece. Next thing is that for the chemists also, do not, do not round down, because we are working with data. Now, why would you round down first of all? Round down, you understand rounding up and rounding down? Rounding up,
Yes.
yeah, rounding up is when you like make the number, like if it's 5 and above, you make it one number higher. But round down is, you make the number less. But here we are dealing with matter. So if you're dealing with matter, if you cut down the numbers, that means you've reduced the matter. And that's doesn't work. We are working with matter. We, for us, that's why I said two places after the decimal is acceptable. Three places is more precise, but generally commonly two places is commonly used. Okay, now let's look at what do you mean by uncertainty. Uncertainty is, um, let's see. Okay, so you have a number here, 1, 2, 3, whatever these numbers are, dot, that's your decimal point, and then some places after the decimal. Okay, so it depends upon the individual who's taking the data, how far you need to be after the decimal. So based on that, you could have let's say you want to have 1, 2, 3, these numbers you need to have in the measurement, and then this number you need in the measurement, but these, it's okay to drop them. Okay, so one place after the decimal would mean plus minus 0.1. In other words, that 0.1, this is the 0.1. 0.1 is signifying this place. Plus minus means like you will go up and down. So when you guys are going to do the labs, you will see it when you take the weights on the machine, the weight fluctuates. Now think about it. When you go in the lab, in the grocery store, and you're buying, let's say, a produce, and you put the produce on the machine, you see that needle, it kind of like fluctuates a little bit, and afterwards the needle stops, but then it's like little bit, it just keeps fluctuating. So that is because it could have be plus or minus, that's where. Let's say if you want, like say 3 places after the decimal. So in other words, you want this, 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 but you want this, this, this also. And you can do away with these. So you can like leave or drop these. So how would you write the uncertainty? Uncertainty would be plus minus 0 point. So 3 places, right? 1, 2, 3. So this is 0, 0, and 1. So these 3 places after the decimal, that is where so the uncertainty is in the last number. It could be 0.001, it could be 0.002, or it could be, less than that also. So that's what it means. Okay, so that's uncertainty. Now, for us in chemistry, I still needed to cover this because, you will be reading some of the data from the apparatuses, just so you know. Now, another thing is that about we talked about the who is taking the measurement. Now, that's another thing. Okay, if you have a graduated cylinder, okay, here's a graduated cylinder, you will be seeing this in the lab, and in this graduated cylinder there's our markings. Okay, now this cylinder, you're being asked to measure some amount of, let's say, 50 milliliters of water. So you fill this with water, and here you fill this with water, and now you try to, take the data or try to read this line. A person who is short, right, is going to read from here. This is the eye. So they are going to read it from here like that. A person who is tall will, will always is going to look at it like that. So both of them may not see the exact same, like they will see the main digit, yes, that's fine, but there is some level of uncertainty, you see, lying here. In that little, like that space, which is like a little bit empty, which doesn't have like the marking. So someone say, oh, it's 0.1, the other person say, no, it's 0.2, like that. So that's where uncertainty builds in. Where should you take the data? So what they have done is they said, okay, well, let's just bring some uniformity here. So you look at the meniscus for the liquids, but even when you do that, because of the height of the person comes into play, and so there's some uncertainty comes into play there. So it doesn't matter, that's why it's not that big of a deal, but we need to still factor in the uncertainty. Okay. Now, that is why we have the significant figures. Like, okay, we understand there's going to be some uncertainty, no matter, how much like precise you are in taking your measurements, there could be some error might come in which is beyond your control also. So then they came up with this rule of significant figures. Okay, so let's keep this is number, this is 4. Okay, significant. What is the meaning of significant? What does significant mean?
Important.
Important, yeah. So significant figures, like I said, these numbers are being used by different people, right? And what number or how many places after decimal is important, and for whom and what, so all that is defined by the significant figure. So first of all, the rules regarding the significant, number one is that all non-zero numbers are always going to be important. I mean, the value, so when we say significant figures, means like what is important, what is valuable. So non-zero numbers are always going to be, so so here I'm going to just use SF. Okay, so non-zero numbers are always going to be significant figures. So for example, you have 2, 4, 3, 9. Okay, so all of them, no zeros, and this number will have how many significant figures? How many? 4. Good. So there are 4 significant figures. Okay, so that means when you are doing the measurements or you're counting or you're calculating, those 4, you are working with 4 important numbers. Those 4 numbers are important. Next is any numbers that is leading zeros. So here you have the leading zeros, not significant, because these numbers can be written in scientific notation. So for example, if you have, let's say if you have this number 0.00121, okay, you have this number. So in this case, these are not important, although they have their own value, but the numbers can be written as scientific notation. So in this case, this number is, this is only 3, 1 to 1, even though the 1 is being repeated, doesn't matter. So these are important numbers. So this is 3 significant figures. Okay. So no matter how many zeros you have in front, it doesn't matter. They're not important. Next is the numbers that are the zeros that are confined. Confined means they are in between the numbers. So they are significant. So they are important. So or in other words, they are counted. So for example, look at this number. You have 1, 2, 0, 9, 6, 0, 8. Okay, all this big number. In this case, although the zeros are here in between, but they are still counted. So they're included in the calculation. So 1, 2, 3, 4, 5, 6, 7. So there are 7 significant figures here. So they are included in counting. Okay. Next is the trailing zeros. Now, this is a tricky part regarding the trailing zeros. Trailing zeros. And I want to give a clarification here because, yeah, trailing zeros, if there is a decimal, if there is a decimal present in a number, then they are counted. They are important. So in a number, so if there is decimal, for example, if you have, let us say 2, 5, this is a trailing zero, 250, okay? And there is a decimal here. So that means there are 3 significant figures. So this 0, because just the virtue of presence of the decimal, is counted. Next is you have number that is, for example, 2, 0, 5, 3.0120. So you see all these zeros are there. There's a 0 here, there's a 0 here, this is a 0 here. So obviously this 0, the one between 2 and 5 is a confined 0. The one that is between 3.01 is also confined, and the last one is the trailing 0, but it is still counted. Why? Because this decimal is present. So presence of the decimal gives value to those zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 significant figures. Okay. Okay. Now, this is the part where I disagree with your book, that the trailing zeros that are, and so be flexible here. In other words, just think outside the box or just look at it in a more. So here they are saying in your book on page 31, and this is part B of significant figures. Now they're saying the trailing zeros, those at the end of a number, are not significant if the number lacks an explicitly decimal point, shown decimal point. So in other words, if the decimal point is not present, then those trailing zeros have no meaning. That's what they mean. So here, and I disagree with it. Why? Because here, look at this, 59, comma, 0, 0, 0, 0, 0, 0, and 0, 0. Such a big number, such a big number. Let's say if this is the population of a town or something, or that's the amount of money somebody has in the bank. I mean, oh, come on, these zeros have a value. These zeros have a meaning. So you look out in that context that, but here's the thing. The same thing can be written as a scientific notation. So based on that, yes, you can remove these zeros. So what is a scientific notation and what is a standard notation? So, and standard. So what you on top is that number is written in the standard form, and the same number can be written in the scientific form. How? Look at this, 59, 59, comma 0. Sorry. 59, comma 0, 0, 0, comma 0, 0, 0. Okay. Now here, even though the decimal is not shown, but it is still present. Where is the decimal? In 59, 0, 0, 0, 0, 0, 0. Where is the decimal?
After the
first
three
zero.
zero.
You don't see this decimal. So this is called implied decimal. And implied decimal is there, we don't see it, but that looks like an exact number. You know, that's another thing. So this is the implied decimal, and this decimal can be moved. Decimal can be moved. 1, 2, 3, 4, 5, 6, and 7. So you move 7 places to the left. And so when you do that, the same number can now be written as 5.9 into 10 to the power 7. So you see this whole thing When you move the decimal 7 places, you can write it in the scientific notation. So from that perspective, yes, these are these significant figures. These can be dropped off, or these are considered to be not significant figures, because the same thing can be written in the scientific notation. So from that perspective, this only has 2 significant figures. So keep that in mind. And which are those 2 significant figures? These ones. 59, 59. Okay, and 59, 2 significant figures right here. Okay, so that's one thing.
Professor, why wouldn't you write it as 59 times 10 to the 6th?
59, no, scientific
No?
notation is always, scientific notation always, that's the one. When we write things in scientific notation, we are trying to condense the numbers and make them as small as possible. So this
Okay.
always one number, whatever number it is, dot and another number. And then generally this is considered, but again, sometimes you may have 2, 3 more numbers after the decimal. And again, depends if you are, whosoever is taking the the measurement.
Okay, thank you.
Thank you. Okay, now look at this number. Another number is, let us say you have another number, which is
Record, please.
which is 0.0000059. Okay, let us say you have this number. So now, in this case, this is also in a way standard form. But when we write it in the scientific notation, we move 1, 2, 3, 4, and 5. So you always have to bring it to like 5.9, like that. So how many places we moved? We moved 5 places to the right-hand side. And when you do that, what do you get? You get
-5.
5.9, 5.9 into 10 to the power. You moved 5 places. Negative 5. Okay. So keep this in mind that when you move it to the right, negative exponent. You move to the left, positive exponent. Okay. So let me put this here. To the left, when you move the decimal to the left, then it's a positive exponent. Decimal to the right, then it's a negative exponent. Okay. All right. So this was about the scientific and the scientific, and because you can write these numbers, as I mentioned, this number right here, these type of numbers can be written in the scientific notation. That is why these zeros, the only value they have is like how many places do you have to move. That's one. Okay. Okay, so that's one thing. Now let's look at the computation in computation. So this was 5. Okay, or calculations that relate to the significant figures. Okay, now 2 types of calculations. One is addition and subtraction together. The rules apply for them the same: addition, subtraction, and the multiplication and division. Multiplication and division. So what should be the final answer? The final answer, when you are doing the calculations in which you're doing adding and subtracting, in that case, your final answer will have the lowest decimal point. So final answer will have lowest decimal point. Okay, so in other words, whenever you're doing addition and subtraction, you are looking at the significant figures, but you're looking at the number of places after the decimal. or number of decimal places. Okay, so when you do that, but when you have addition, multiplication, and division, then in that case, you look at the these lowest significant figures. So the answer has the final answer has the lowest significant figures that were used in the computation. So when you're doing multiplication and divisions, you're going to look at the numbers, and you're going to bring in the or count the significant figures in this case. Each number has. So the final answer will have lowest. Now, based on that, I'm going to just add in here another important aspect, which is rounding up and rounding down. So based on that, we will have to do this. So rounding up and rounding down. Now, rounding down, people who are like, estimating, then they round down. Like, for example, you have 109, your guests are coming and 109 people are there in the party, and a chef is trying to make food. So I say, okay, I just need to estimate. I'm going to use 100, okay, for mental math. So those numbers are like for quick estimation. So rounding down is used, but rounding up, because we can just factor in some uncertainty. So that's why rounding up is used. But we never round up and down when we are doing the calculations, like on these different steps in the calculations, we just keep the numbers raw. It's only the rounding up and down is only going to be for the final answer. Final answer. Only in the final answer. So do not round up or round down, in the steps in the calculations. So otherwise you will introduce a lot of rounding up and down is already introducing uncertainty. Like some error is coming right there. So don't do it in between the steps. Okay. Anyway, so when do you do the rounding up? First of all, you should know how many significant figures you need. Okay. So get that. Next is you you drop the number. Oh, no, wait a minute. How is it that the number you want to keep, you look at the number that you want to keep. Look at the right side of the number you need to keep. And that decision comes from how many significant figures you want or should be there in your final answer. Okay. Once you know that, now if that number is 5 or more, you round up. Okay. But if it is 5 or less, then you keep as is. If it is less than 5, it will remain as is. And less than 5, keep as is. Okay, so we will see this in a minute. All right, so now let's do these calculations based on the addition, subtraction. Let's see if I can get some numbers from the back. Yeah. Okay, we'll look into that one. So that is number 49. Okay, so let's do this. Okay, one is number 49 is multiplication and division, but I'm looking at something. Where is it? 48, 49. Okay, carry out the following multiplication, division, expressing your answer. Okay, this is one thing. Let's do addition, subtraction also. So addition, subtractions, we can do like maybe 52 or 51. If there's any, okay, let's do number 49. Which specific, there are 4 of, there's. Who's talking? I thought, okay, okay, go ahead. The last one is F. F. Okay. Okay, so let's do this one. So this is 49F from the book. So let's do this page number. Page, see, I know some people told me about the ebook. There are some differences in the page numbers, or there's some discrepancy in the numbers, but the questions are still the same. So page 52C, and this is the problem number 49, and we'll do F. Let's do this first. Okay, 4670 multiply by 3.00 divided by 2.450. Okay, all right. So when it's a multiplication division, then we see that we are going to use the final answer will have the lowest significant figure. So final answer should have the lowest significant figure. So which means now we are counting the significant figures here. So this guy, exact number, right? This is an exact number, and this will have, and there's no decimal. So that's the tricky part, because this could be 3 significant figures, but this could be 4 significant figures also. So let's keep it at that, 3 significant figures. And it can be 4 significant for, okay, here's something you guys should, this is not in your book, make a note of it here. Where did we do this? For the exact numbers, it varies, it's variable. This point, put it here. This is 5 here and 6 here. Okay, for exact numbers, the significant figures are variable. This part is not in your book, so please write this down. Significant figures are variable. They change. So in other words, because it can be written as scientific notation, that's why. So in other words, for example, if you have 100 and if you have 1000, so this could have like multiple significant figures. So this could be 1 significant figure, 2 significant figure, 3 significant figure. This one can have one significant figure, 2, 3, and 4 significant figures. So that's the way it is. Okay, so for all exact numbers, it's variable. So with that said, now here you have an exact number. This guy is an exact number. This, and this here, and then it's a trailing 0. So that's why I said it could have 3 significant figures. It could have, if you write it in scientific notation, it could be 2 significant figures. It could be 3 significant figures, just 4, 6, 7, and then it can have the 4 significant figures also, because you're including the 0. Okay, so that's variable right here. Next is this, because the decimal is there, so they are definitely 3 significant figures. Okay, this guy, again, because the decimal is there, so this 0 has a value, it is counted. So 1, 2, 3, and 4. 4 significant figures. Okay, so now with that said, your final answer, because the question is not saying that write the answer in scientific notation, so obviously your final answer should have only 3 significant figures. Final answer should have 3 significant figures. Okay, now you guys do this math, do it on your calculator, tell me what numbers do you get. 4670 times 3.00. Must get that. Tell me, what do you get that? Get that number. Yeah.
Have to have it up.
Like how do you, okay, 4670 times.
Una loca me está llamando que es el domingo allá en la piscina.
Oh, mute yourself, guys.
Please. No, I know. Well, we ain't got no plan, so tell Papa. You tell Papa. Ya le dije. What did he say? Le dije por el niño, ¿no?
Okay, so I muted you guys, so anyone has to speak, then you guys just say, okay, yeah. 4670 times 3.00.
Yufang wrote it in the chat. 5718.367.
Yeah, 57. So give me, okay, 575718. So this is the number you see on your calculator, 0.367. Do you have anything more after 67? Okay, just leave it like that. Okay, so this number divided by 2.450. Give me like huge, big, whatever number you get. Oh, that's the final answer, Yufang? Okay, okay, Yufang already did this. So from the calculator, we see this number, 5718.367. Okay, but according to the rules, your answer should be only 3 significant figures. So what are we going to do here? We will have to convert this into scientific notation. That's the only thing. So are you sure you got this number? After dividing also? Okay, okay, okay. So now the final answer, carry out the multiplication expressing your answer to the correct number of significant. They haven't mentioned it here, but the only way you can get the final answer, the correct number of significant figures, is if you convert this to the scientific notation. So the way to do that is 5718.367. So 1, 2, and 3. So this is one way of doing it. Okay, so 5.71. And I'm going to we'll cover this in a minute. How many places did we move? 1, 2, and 3. We moved 3 places. So 10 to the power 3. So it should be positive or negative?
Positive.
Positive. Very good. So next is we need to have 3 significant figures here. 1, 2, and 3. So we are keep 1, but drop 8. But 8 is more than 5. So in that case, what does this become? This becomes 5.
5.72.
Yeah, 7, 2 into 10 to the power 3. So this is in terms of scientific notation. If the question, the right way of doing it is this, but there's also a more common other way of doing it is 5. So this is scientific notation, which is like more, because it's a very big number, so more appropriate way of writing. Other way is 5718. Now we need to make this into 3 significant figures. 0.367. So obviously these will be drop off. Okay. So how do you make this into, so that means we would need 5, we need 7, and we need that, you know, like 8. So 5720, that would be the right one. So this gives you 3 significant figures. And again, according to that rule, because this is an exact number, so it can have 3 significant figures or it can have 4 significant figures. But the final answer only wants 3 significant figures. So that's another way of showing it like that. So it's all been like, in other words, it's been like rounded up. Okay.
So both of these can be the answer.
Yeah, both of them can be. If the question is asking in significant figures, then this is the right answer. But if the question is asking, put it in the scientific standard notation, convert this into the standard notation, then you do this. Okay, why is there a 0 in the end? Okay, here's the thing. Okay, you use a little like kind of how do I say this? Like, okay, use this comparison 5718 and 57. So if you say, okay, so 572. So these two numbers are different or not? Right. So this is obviously a very big number, like thousands, and this is only in hundreds. So you don't want to lose just because the question is asking you like find the answer in the significant figures. You don't want to lose the value of the number. This one has lost the value, right? So that is why zero. That is why zero can be dropped off, or value like zeros is, that's why there's a flexibility in zero. So that's why. Got it? Okay, good. Okay, so that was multiplication, division. So we covered that. That was a good example. And let's cover, you have any other one you guys want? Any other example from the back? No? Okay, I'll pick one. So this was the, let's do this one. 2.2, 2, like 2-52, and again page is 52C. Okay, so let's do this one. C, and this problem number C, that is 235.45 plus 37. So put 37 here, plus 36.4, 36.4, and you have to add this, all of these. Okay, so here addition and subtraction. So there are 2 decimal places. Okay, this is 1 decimal place, and this guy is kind of exact number, so it's variable. It doesn't apply, in other words. So in this case, the decimal point is not applying. Okay, so your final answer should have only 1 decimal place. Okay, because that's the lowest one, it should be there. So this one. Okay, now we just add. So 5, 8 point, what is this one? 12, 13, 14, 15, 16, 17, 18. So 9, 10, 3. So this is what you get. Now we need to, because the final answer only one significant, 1 decimal point. So we will have to, again, in this case, this is 5. So this we need to keep this, but round up.
Professor, you accidentally put 0.
Huh?
You put 308.
308.
It's supposed to be 398, right?
39. Okay,
Yeah.
I made it wrong.
No, I got 308.
See, yeah,
Yeah, I got 308 too.
yeah.
Okay, never mind.
Okay, so we need to keep, because of this rule, we need to keep 8, but we need to drop 5. So that means 8 is rounded up to 9. So this becomes 308.9, because we only need 1 place after the decimal. Okay. So, these significant figures are important because you need it for your Chem 1A class also, or another class. Okay. Now let's look at the conversion factors, equalities and the conversion factors. And so this was one example. This is another example. Let me put this here. Example. Okay, 6. Okay, next is the, okay. Now we have to look at the equalities and how to use them in conversion factors and dimensional analysis. Dimensional analysis is a technique, where you take the one unit and you convert it into another unit. Okay, so in this case, let us say, let's do some conversions. Let's look at some equalities here. For example, you have okay, let us say you have 1 inch example. So here you have 1 inch. 1 inch is equal to 2.54 centimeters. Okay, so this is called the equality, equality. And this equality can be written into 2 conversion factors. Now this is very important because you would be needing this in throughout the course. So understand this. So equality can be converted into conversion factors. What are those? 1 inch over 2.54 centimeters and 2.54 centimeters over 1 inch. Okay, so this is the 2 ways you can write this. So how would you use these conversion factors? So whatever is given to you, whatever unit is given to you, you're going to write that down. So given unit in the question, okay, from the question, in the question, you write down the given unit, okay, multiply by that conversion factor which cancels out that unit. So the unit that is given to you is going to be, at the bottom or in the numerator, in the denominator, and the unit that you need to find or convert to. So here is your find unit, or the one that you need to convert to, and this is the one that relates to the given unit. How do I do this? That relates to find, and that is just relates to the unit that is given in the question. And so why do you do this setup? So the given units and the one that relates to that given unit cancels out. So we will look into this in some examples we will see. So this way those cancel out and you get the only units that you need to find. Similarly, look at one example here for mass, which is 1.00 pounds. 1.00 pounds is equal to 1.00 pounds is equal to 454 grams. Okay, so that's the equality, and the conversion factors are 1.00 over 454 grams, or 454 grams over 1.00 pounds, 1.00 pounds. Okay. Similarly, if you have volumes also, now I'm going to just do this volume. 1000 milliliters make 1 liter, and the equalities are 1000 milliliters over 1 liter, or 1 liter over 1000 milliliters. Okay, so these are the different conversion factors, the 2 types. Okay, now let's look at the examples. Now, you guys have any questions from the back? Anything you want me to specifically do? No? Let's see. So that's actually the dimensional analysis part. Convert the following. I gave you. Okay, let's do this. Page example from the back of the book is page 50E. Okay, and this is the problem 2.90 or 90 problem. And here, let us say you are given the equality 1, and we will give you these equalities, or you will refer them to the handout. Okay, so 1 pound is 4 53.6 grams. Okay, so how many, when each of the following measurements mass is converted to grams. Okay, so here let's do these two, and do it and find the answer in significant figures. So find the answer to correct number of correct significant figures. Okay, so here you have part B. And in part B, you are given 3.2091 pounds. Okay, convert that to grams, or how many grams is that? So that's a question. And then find the answer in significant figures. So, okay, always write down your equality. We know that this is known. We know, or will be given to you. We know that from the tables, you know, or will be given to you, that 1 pound is equal to 453.6 grams. Okay, so the conversion factors are 1 pound over 453.6 grams, or 453.6 grams over 1 pound. So write down the given, which is 3.2091. Write down the unit. This is given to you, pounds. Now you need to find how many grams is that. So find the grams. Grams goes on the top. Pounds is going to go at the bottom, because that's what you need to cancel out. So you are going to use this conversion factor, because this conversion factor is allowing you to convert, like cancel out the pounds. So your 1 pound is at the bottom, and put here exactly as it is, 453.6 grams. Okay, and so here you are going to take pounds, and pounds, you see, cancel out, and you are left with 3.2091 times 453.6 over 1. So even if like 1 doesn't mean anything, but still write it down. Now, because it's a multiplication, we are going to use the lowest significant figures. So this is 4 significant figures. This one is how many? 1, 2, 3, 4, 5 significant figures here. So multiply, tell me, what do you get? What do you get, guys?
Hold on. $1455.647.
Okay, good. Now, according to the rules, because the question is very clearly asking, find the answer to the correct number of significant figures. And according to the rule, the correct number of significant figures would be, in this case, 4 significant figures, right? We need 4. So we need to keep this, we need to keep this number, we need to keep this number, and we need to keep this place also. Now, because this number, we only need 4, and these guys we need to drop off, and we see that 6 is more than 5. So what happens to this 5? This we are keeping, but what happens to this one? It gets rounded up. So your answer now is what?
1456.
1456. And don't forget the units. That's why you did all this, to convert, right? Okay, so that's how, you know, you do this. So, you know, I think if you have anything else, you can ask me, but generally, you know, we just have the density, and I think the temperature also. Okay, so that's the algebraic conversion. Density as a conversion factor. So this is the 7. 7. So here's the density as conversion factor. So in other words, you can use the formulas also to use them as a conversion factor. So here's the density. Density is equal to mass over volume. Okay, mass over volume. So now break the whole thing up. This means that for, let's say, density of water, the density, okay. If you are given the density of water, now by this time, water, you guys should know this, H2O, that's water, is equal to, now again, I'm not going to be writing WATER. Okay, so here, 1.0 grams over, sorry, if you're just given this, what does this mean? 1.03 grams per milliliter. This means that 1.03 grams of water equals 1 milliliter in volume. This is what it means, because density is mass over volume. So in other words, whatever amount of mass is, that is equal to whatever the volume comes out to be for a substance in general. Okay, so for here, these are the two conversion factors. This also means the equality in this case is 1.03 grams is equal to 1 milliliter. This is what it is. Okay, so again, the conversion factor is 1 milliliter over 1.03 grams. So you see, you have taken a formula, converted that to equality, and then created the conversion factors. You see that? Okay, next is if you're given the volume, you can find the mass. If you're given the mass, you can find the volume. So let's see, one example I can do from here is state whether each of the following will rise or sink. Okay, let's do this, and you will do this in the lab, but let's see, this is the 2-98, page 52E, and this is an example. Okay, here you are given the air has a density of 1.29 grams per liter. This is the density of air, okay, at room temperature. State whether each of the following will rise or sink. So if you are given helium gas, so helium gas, will it rise or sink? Helium gas has a density of 0.18 grams per liter. And you're given an argon gas, again, this is another type of gas, and the density is 1.78 grams per liter. So here is your this is your like a reference. With respect to air, if the helium gas comes in, the density, so to compare the density, because the density of helium gas is less than that of air, so therefore it will rise. Because the density of helium is He, argon is HAR, okay? So helium of density of helium is less than the density of air. So it will float. It will rise high. But argon is going to sink because the density of argon is more than the density of air. Okay, so that's one way. Similarly, you will be looking at water and oil and those things. Let us see. A sample of the sand is found to have a mass, volume, acetone. Okay, let's do this one. Another example is 2.93, page 52E. So here you are given acetone, you know, the one that is for nail polish removers, right? Okay, so this acetone is there. It has a density of 0.791 grams per milliliter. Okay, so this means, first of all, this means 0.791 grams is equal to 1 milliliter. Per milliliter means 1 milliliter. Per milliliter means 1 milliliter. So keep that in mind. Okay, the conversion factors are 0.791 grams over 1 milliliter. And the second is 1 milliliter over 0.791 grams. So two conversion factors. Now the question is asking, what is the volume in milliliters? Volume, find the volume in milliliters of 20 grams of acetone. If 20.0 grams of acetone is given, then what is the volume? So you are going to just see out of these. You need to find the grams. No, sorry, you need to find the milliliters. And grams is given to you. This gram is given to you, 20.0 grams. And you need to get rid of grams. And you need to convert that 20 grams to milliliters. So you will use that, you know, conversion factor. So another thing, just for the conversion factors, numerator are the top numbers and denominators are the bottom numbers. And denominators always should cancel out. Denominator, that is why they are at the bottom. So cancel out the denominators. Okay, so then you will be left with the numerator. So anyway, so here you write down what is given. You're given 20.0 grams, multiply by the conversion factor 1 milliliter over 0.791 grams. And so here you see this grams and grams cancel out. And so what are you left with? You're left with 20.0 divided by 0.791. So 3 significant figures, your answer should have 3 significant figures. So what do you get here? Say that again.
Would it be 25.3?
30,
25.3.
okay, 25.3. Yeah. So this is going to be milliliter. So just don't forget, you know, the units. So let me make this here. Do not forget to place the units. Okay. Okay, so that's one thing. Now comes the the other one is the conversions of the, yeah, we are behind, but it's fine. So 7 and 8. Temperatures. So here's another thing, guys. On your handout, I do not have the conversion, like the formulas listed, but you can write this down. It doesn't matter which ones, but you can always, you know, if you are given degrees Fahrenheit, I mean, you need to find degrees Fahrenheit, then 9/5 multiply by whatever degree Celsius is given to you, plus 32. So here, remember that, PEMDAS, please excuse my dear Aunt Sally. So in other words, parenthesis, exponents, multiplication, division, addition, and subtraction. So that's the rule, right? And then the other one is degrees Celsius. So you should write this down in your handout. 5/9 And this degree Fahrenheit that is given to you minus 32. Okay. And then if you're given something in degrees Celsius plus 273, and that converts to Kelvin. Or if you need to find if you need to find a degree Celsius from Kelvin, so you're going to take the Kelvin figures minus 273. So keep a note of these. So let's just do one example. Okay, temperature scale. What is the temperature? I'll just do this one, 103. Example. Um, 2-103, and that's page 52F. Page 52-F. Okay, here you are given 525 degree Fahrenheit, 525 degree Fahrenheit, and they're saying, fine, what is the temperature in how many degrees Celsius is that? So convert Fahrenheit to Celsius. Okay, so you're going to use the formula degree Celsius is equal to 5/9 times degree Fahrenheit minus 32. So first solve the parenthesis. So write down here 525 minus 32. Whatever number you get, that is multiplied by 5/9. So what do you get here? 5 plus 32. Which one? Did I make a mistake?
493.
Oh, this one is 32, guys, not 33. Thank you. 32. So what do you get? This is 493, the parenthesis?
Yes.
493. Multiply by 5, divided by 9. That's another way of doing it. Then that gives you the degree Celsius. Okay? Clear? Any questions? So this finishes your chapter, and I wanted to start the second chapter, but tomorrow I'm going to do this. So, you know, I know we are moving fast, but don't worry. Just do your best.